Hello again, and welcome to our series on Cisco security integration into ACI Fabric. Today, we're going to show you how to set up ASA cluster in ACI. We're going to go through some slideware and go into a demo of setting up two ASAs in a cluster and then orchestrating our firewall policy through APIC itself. My name is Goran. I'm a technical marketing engineer with Security BU at Cisco. Cisco security functions integrate well into ACI Fabric. We have an ASA device package that integrates both physical and virtual ASAs, and we also have a firepower device package that can integrate standalone virtual and physical firepower appliances into ACI Fabric. In this video, we're going to show you clustering that is supported on the 1 gig and 10 gig appliance that you see here with their integration into ACI Fabric, and that integrates our ASA traditional firewall as well as our firepower services that provide you threat protections and NGIPS policies as well. ASA has two flavors of clustering. The one that works with ACI Fabric and is the first hop redundancy provided by ASA span cluster. So for the span cluster data plane, we have a couple of options in terms of attachment here. All of the data plane interfaces for ACI integration are VLAN trunks, and our best choice and recommended is to leverage dual attached ASAs with span port channel working with VPC on 2 leaf switches, as you see here. This provides us the best redundancy in place, where we have good port redundancy within that port channel group, and also we have leaf redundancy itself. So if one of the switches actually has a problem and goes away, our cluster is intact because it's also attached to the left leaf that you see here. What we cannot do with ACI Fabric today is leverage individual port channels into their own leaves for every ASA unit. And this is because APIC only manages the master ASA and can only configure that port channel there. We can, however, attach each of the ASA units to a single leaf switch and have that single port channel there be spanned from the ASA Appliances, and also coming into that single port channel on that leaf 101, as you see here. This particular deployment does not provide us leaf redundancy itself. So here, when we have all of our deployments, the data plane with service graphs, we actually get APIC to orchestrate the data plane by configuring VLAN subinterfaces on top of that port channel or virtual port channel, and it does that only on the master, while that configuration is replicated through all other ASA slave units. To do this properly, all of the ASA units have to mirror their own data plane attachment with ACI Fabric itself. In terms of the control plane for the cluster, we on the ASA side have to use an untagged links here, and our again recommended attachment to the fabric is to leverage VPC. So each of the ASAs is dual attached to couple of leaf switches, and in this case we do identify that CCL as a single port channel on all the ASAs, as for example I'll show you port channel 22, but on the leaves themselves they are separate and unique VPC IDs. There's a unique VPC ID per ASA unit itself. We can also attach each ASA individually as a port channel to its own leaf. This doesn't provide leaf redundancy in that case, and third option here is to actually leverage a single interface into the leaf. That's obvious what sort of risks this kind of deployment carries, because we do not have redundancy of multiple ports for control plane with each ASA, and we also don't have redundancy of leaves themselves in this case. So to get the cluster control plane up and running, we actually have to create an EPG for CCL and add all of these static paths into that EPG so that all the ASAs can actually talk to each other. Again, this particular attachment has to be mirrored across all ASAs for cluster to work. So looking at the cluster configuration itself, it's good practice here to start with clearing the whole configuration, enabling the cluster interface span mode. This is as opposed to an individual mode cluster. That's another option for customers, but again, individual mode is used for different purposes, and you can find a video by our colleagues in the data center as well that had validated the individual interface mode cluster with dual fabrics themselves. Basically having two different fabrics in two different locations and one cluster carrying the state of connections across both sites. So back to our cluster here, we enable the span cluster, and this CLI would require a reboot. However, you can force that without the reboot because we had cleared the configuration prior. Again, MAC address auto prefix is important for multi-context mode, which I'm assuming this ASA is already in that mode. And then we proceed to configure the cluster control link. Here I'm adding this interface into the port channel 22 as LACP. That's the mode active here designation. We do no shut for that interface. And finally, we have our cluster group configuration. We have these three commands be unique per ASA unit: its name, the cluster interface IP address, as well as priority, which should be unique per every unit, so we can elect master, unique master in any case of failures within a cluster. And we have the rest of the CLI that basically is replicated between all the units from the master, and enable actually turns on the cluster and tries to sync into the cluster that's already there. You can get more details on all the CLI in ASA Configuration Guide, the chapter on high availability. So ASA Multicontext is a feature that virtualizes firewalls, enables us to segment customers that have their own independent policy, interfaces, routing table, or VRF, can manage those contexts independently and register them into APIC independently. Each firewall can be either transparent L2 or routed L3, and all the contexts would share the common data plane port channel that goes over VPC for best redundancy with ACI Fabric, and they share the cluster control plane that we just mentioned, as well as their own firepower module that's installed in those chassis in the cluster. So these contexts are all defined within the system configuration once you actually change your ASAs into multiple contexts. We do define and mark one of the contexts as admin context that provides root access, so you can switch into any of the contexts. And inside that system context, we can define the context interfaces, its own configuration that can be on or off the box, and all the user contexts that are supported to max of 250 on our top end 5585 SSP60 appliance. Each of these contexts has to be pre-configured so we can talk to APIC via SSL channel, and this is the config that you have to apply there so that those two can start to communicate and APIC can register this context. If any of the context is designated to be in transparent firewall mode, you ought to convert it into L2 mode before applying this configuration itself. So in this slide, we are showing you that design with high availability in mind that leverages clustering from ASA, our active-active model, with the VPC on two leaf switches. So ether channel and multiple contexts leverage to basically give us the best high availability and also segmentation within our solution here. This includes also our firepower integration into the ASA Appliances and your ACI Fabric. So once we install that ASA device package into APIC, our particular topology here includes our pre-configuring the cluster of two ASAs that we see here. On the bottom we see our control plane, which is a single port channel on ASAs, but individual VPCs for each ASA unit. And then we have our data plane that you see here as a single VPC, VPC3 on the leaf switches, and single spanned ether channel across the ASAs. And we have that cluster in place. The ASA device package allows us to register our administrator context and user context to different tenants within APIC. And once we render that service graph in the fabric for a particular tenant, APIC will configure these sub-interfaces, dynamically selecting the VLANs, configure them and attach them to this context, and apply the full configuration on the master pod 1 context in this case. This config is synced to all the physical slave units that are in the cluster, and that means that same context exists on all the other ASA units. So as the leaf switches load balance traffic to any number of ASA units in the cluster, any of those units can handle that traffic. In fact, a particular connection is owned only by one ASA in this cluster, which ensures that all the packets are actually fed back to that unit and passed on to the firepower for full inspection and full context of threats. So you can also see that there's a firepower piece here. So what happens, we can actually, as part of the ASA device package, redirect traffic to the firepower inspection, either inline or promiscuous. And our firepower management console that you see on the right is registering these sensors that are embedded in ASA Appliances. The sub-interfaces created by APIC will actually show up in that management console and allow us to actually segregate them into their own customer and apply a unique policy in terms of malware, NGIPS, or access control as well. So this particular ASA device package allows you to set up an ACL and redirect a slice or all traffic to that firepower. This gives you some ability to actually do some optimizations around what traffic you want to see deeper inspection on. So to our demo now, what we're going to show you is how to set up the cluster of two ASAs. We will also register administrators context into APIC and show you what's needed to get the control plane running. And then we're going to create this user context pod 1, which through some programming and scripting with Python to APIC, we are going to orchestrate the whole tenant with its ASA in the path. So you can see here our web EPG is going through ASA to get out of the fabric to this outside network. So we're going to put all of these pieces in place and allow our ASA context to peer with the fabric and learn about these two routes that you see here. This is all enabled by ASA device package, where we highlight this L3L dynamic peering. We'll leverage OSPF in this case. So with that, let's look at our APIC here. I have a common tenant here in place that has this application profile, and EPGs here that you see are all based on the control plane. So this CCL EPG that I have here is enabling our cluster ASAs to speak to each other. And if I look at its static bindings, the paths here, I have placed our two individual VPCs for ASA 1 and 2 into this EPG and put an incap VLAN 20 untagged so that these two ASAs can talk the control plane. In the previous videos that I've done, I showed you also failover setup, and here are the two failover EPGs. So this is a LAN, and these are the two interfaces in a different VLAN untagged, allowing two ASAs in failover to talk to each other. Similar here for the link. It's a different VLAN and a different ports that are in place. So if I look at my layer 4 through 7 services here, and I have my devices here, I have my cluster in place. So this is administrator's context that is registered with its data plane of port channel 10, which is a VPC, and its address is actually .20 here. So if we take a look at our ASA appliances here that we have in place, we have 2 units here, and the right unit here that I'm on the console is a slave unit running 951 code, and the left is actually a master unit that you see here. So what we're going to do now is we will take the easiest way to kind of demonstrate this for you is to put the wrong IPs in here and make APIC think that it cannot reach this ASA admin context anymore. So here, that's the device state is init, which means it cannot reach it. And if I look at that particular context real quick on the master, I see that my address on the master is actually .20. So if we now proceed to actually rebuild this cluster, I am going to get out of these consoles here. And I'm going to run a script that's going to show you how to set up both of these units. So this script is going to clear the configuration on the master first, rebuild it, and then proceed to the slave unit. So here's that clear config all, and we are actually configuring the control and data plane, and then switching into an admin context where we clear the config again and set up the local pool for its management addresses, as well as the rest of the config necessary for APIC to reach out to this context itself. We have already logged into the secondary, so what we can do, we can go back into our units, and we see here that's our master to be, and here's our slave unit. So here, if I do show run cluster, I can see the configuration for that unit is already there and it's enabled. And if I do show cluster info, I can see that we have on call, and this unit had just become a master. The other unit discovered the master and it's syncing the configuration. And those two are gonna quickly become master slave, or they're become 2 ASAs in a cluster. So I am waiting here to see this message that says cluster unit ASA2 transition to slave. So if we do show cluster info again, I see that one unit is a master and the other unit is a slave. So we have our cluster built with our admin context again. And if I go into that admin context again, I see that it's a .20 address that's in place there. So what we're going to do next is go back to our APIC. We're going to change our address to 20, and we'll submit that, and we'll see if APIC can reach out to this newly created admin context. It says it's stable, so it's able to see it, and in terms of these faults, this is already cleared, so that's not an issue anymore. So we have our admin context registered. What we'll do next is get out of the master, because the next step, we're going to pre-configure all of the contexts that are going to be segmenting our tenants on this single cluster in, to different service graphs. So with that, I'm just going to run that on the master, because that config will actually sync up to the other unit. So if I do show context, I see pod 1 had been created here. And we're just going through the loop of creating each of these contexts. If I do show run context, you can see the CLI I showed you in the presentation earlier. And if I get into pod 1 context, which we'll use here, I can see that its IP on the slave is 142. I can also run CLI cluster exec show IP, which will go to the master unit as well, this ASA1 unit, and show me that master IP is 10.10.10.31 in this case. So if I look at a few more items here, I don't see an access list in place for this unit, and I don't see any routes in place besides management routes currently on this pod 1 context, and I'm checking this on the slave itself. So I will stay in this unit here on the pod 2, and what we're going to do next is we are going to show you this script that we're going to run for programming the APIC itself, and it's a Python script that you see here, and I'm going to build tenant applications with the TPGs, bridge domains as well, build a layer 4 through 7 device for this pod 2 context that's part of the cluster, and then we'll build a function profile for the cluster, service graph, L3 out, and kind of do some cleanup that's necessary to do for the wizard that's in place to make this device L3 attached to the fabric itself. So let's go ahead and prep that script. We're going to go back and look at our tenants here. We don't see a pod 1 tenant in place yet. So as we run this script, we'll see that that pod 1 tenant actually gets created right here. We can double click to get into it. We can see that we have our application profile with 3 EPGs. So I am going to open layer 4 through 7 device folders here and continue our automation. So we had just created our cluster and the function profile for that cluster. If I look at that device here, I can see that it's a .31 IP of that pod 1 master IP, and this is the admin context that we registered in common. This is how APIC gets in to assign interfaces into this context pod 1 once the service graph is actually rendered. If we keep going here, we're going to create service graph, the L3 outs that are part of this, and then do all of the cleanup and the rest that's needed for that wizard. So at this point I can take a look at the deployed devices, and I see that actually I have that cluster in place. If we go and take a look at our slave again, we can look at the routes, and we can see that we don't have OSPF peering yet in place. But we do have our new IP addresses based on those 2 same subinterfaces on a big data plane port channel. And we do have access lists in place. That's what's been assigned in the function profile itself. If I look at that, just to match up the access list here, I can look at the function profile, and I can see, for example, since I set this shared column to true, I can modify these ACLs on the fly within APIC, and they'll get reflected on the ASAs themselves. So if I look at this access list here, I can see that I have my HTTP, SSL, ICMP, and UDP. So what I can do is actually go in here and change this service to SSH. So once I click submit here, you can see this web www destination port will be changed to SSH. So once I've done that, if I look at, I see that right here, if I show that access list again, it had changed to allowing SSH now. And if I look at my routes again, by now we had established peering with the fabric itself, and you can see those OSPF routes in place. So with that, what I can do now is I can go into my master as well here and change into pod 1 context. I see the same information, and I don't have, I basically have some connectivity already in place. So if I look at my example connections here, what I have in place is I have some connectivity between my outside box. So going back to we have our outside Linux that goes through its gateway through the fabric L3 out to ASA, SVI on the web EPG to this web Linux here. So right here is my outside host. I have a ping going from the web host to outside, and right here from the outside box here I have a UDP connection that's coming here. That's what you're seeing here shown. What I'll do also is I'll open up an SSH connection so that we can have a TCP connection also to test with. So here I have my SSH connection, and if I do my show connection output again, what I can see is that this master ASA is actually backing up my UDP and TCP connections. That's what this Y flag stands for. And if I look at show connections on the slave, I can see that it's actually active unit for both of those connections. So this is great because what we can do now is we can test if we actually have a failure in this unit, how the UDP and TCP connections are picked up by the other unit that's in the cluster as well. So let's go ahead and do that. So we have our pings going, our UDP. We'll give them a little space here. And what we'll do here is we'll simulate the crash on this unit. And see what happens. So right here I'm simulating the crash. I see that the other unit had picked up that the other unit disappeared. And right here what we'll do is we'll quit our UDP, we'll quit our ping, and we'll see if our SSH connection is still in place. And yeah, I can see that I'm still there with my SSH, so that didn't see any hiccup there. And if I go back into looking at my UDP connection here, I can see that I had lost roughly 2 seconds of communication going through. And if I look at my pings here, so no pings were actually lost, but TCP basically kept going. Only the UDP, few packets were lost there. I thank you for your attention and hope this was useful for you.